Hi everyone, I'm Yongjun. Thanks for the introduction by Smolly. It's my pleasure to present our ATC paper, Resource Multiplexing in Training and Serving Large Language Models. This work was done in collaboration with Haofeng, Yao, and my supervisors, Anna and Gustavo. With the advancement of open source generative AI, self-hosting large language models in on-premise or cloud servers has been an attractive alternative to cloud APIs. Let's take a look at some popular options for self-hosting LLMs. With AI PCs like a DGX Spark, users can run LLMs with up to 200 billion parameters locally. With AI workstation like a DGX station, multiple team members can fine-tune and run IP-specific models on demand. Small and medium-sized organizations use on-premises servers and cloud servers to host LLMs for their users. This is the famous chatbot Arena and the team behind them. So now we introduce the main function that user will be used to interact with LLM. State of LLM serving system accelerates LLM inference by separating it into prefilling and decoding phases. The prefilling phases generate the first new token and stores the KV cache tensors representing the model states of the input tokens. And the decoding phases utilize all KV cache tensors to generate a new token. And by reproducing real-world traces using the state-of-LLM serving engine and profiling, we make the following observation. First, the decoding phase of LLM inference is memory-bound. Since generating even a single token requires loading the full models from HBM into SRAM, so it has low compute utilization. Second, the request loads in all inference workload fluctuates greatly. So if you are personal users or small and medium-sized organization, you will likely need to waste extra money to over-provision your GPU resources. And for self-hosted deployment, parameter-efficient fine-tuning is a very popular choice because if you do full fine-tuning, you may need to prepare dozens of times of more GPU resources to serve different downstream tasks. Parameter-efficient fine-tuning techniques freeze the pre-trained model and update a small number of parameters, which can reduce the number of trainable parameters by a factor of 100 to 10,000 times. Take LoRa fine-tuning, for example. LoRa hypothesis that the update to the weights have a low intrinsic range during adaptation. We also make below observation on PFT by profiling, using the state-of-art fine-tuning frameworks, collecting information for Hugging Face and multiple cloud vendors. So we have this observation. First, overall, both the forward and backward parts of the fine-tuning are compute-bound. Second, users need to execute fine-tuning frequently. For each downstream task and each new model, users need to do fine-tuning. Once new data from the last few days comes in, users need to repeat fine-tuning again, which is called continuous learning. Third, the latency of fine-tuning is more relaxed compared to inference, which has 50 to 100 millisecond latency SLO requirement. Lastly, parameter-efficient fine-tuning can share a base model with inference tasks because it only updates the adapters. Considering the low GPU utilization and LLM inference workload and the computational characteristic of LLM inference and fine-tuning, we would like to ask, can GPU utilization be improved through resource multiplexing between LLM fine-tuning and serving? This urgent need is also mentioned in a recent paper from Microsoft Research, the title of which is listed here. So we try to solve this problem using existing solution but failed. Let's look at the temporal multiplexing. So here, this arrow means that you have arrival of new inference requests. And then you need to do prefill first, which is the green rectangle, and then you need to do decode. And if you finish your inference request, you can do fine-tuning because there's no other request. And you do the forward parts of fine-tuning. If during this time another new inference request come, you need to stop it, suspend it, and then you can do prefill and decode again, which is the green and yellow boxes. And then you do the backward, which is the fine-tuning backward, because we do the fine-tuning forward a few milliseconds ago. And then if there's no request, you can do fine-tuning continuously. However, when you're doing backward, which takes a long time, there may have some inference requests come in, and then you need to wait the user need to wait a long time until they can see the results of the inference requests, which lead to high time to first token. So we can also use spatial multiplexings like multi-process, NVIDIA multi-process services. And then you can see if you don't limit the GPU resources on the fine-tuning task, then you will have a high time to first second and time per output second, because the fine-tuning will use most of the resources. But in the same time, you can do some limitation on the GPU resources allocated to the fine-tuning worker. And then you can have a good TTFT and TPOT. But the result is that there are some GPU underutilizations when the inference request load is not that high. And there's also other solution like NVIDIA multi-instance GPU. The inference and fine-tuning are isolated. But this solution is not memory efficient because they cannot share the base model between different tasks. And each base model may be hundreds of gigabytes. And we try to stop this, and we to solve this problem, where we propose an LLMStation. So in this figure, you can see that we can achieve a good high GPU utilization while guarantee SLO, and then we will show the idea behind this system. Here are the design principles behind this system. We focus on 3 parts. The first one is SL guarantee. The co-execution of a parameter-efficient fine-tuning LLM inference should not violate the performance SLOs of LLM serving. The second one is GPU utilization maximization. Our primary objective is to maximize the GPU utilization in each short time slice to improve PFT throughput under the highly fluctuating the real-world LLM serving workload. The third one is memory efficiency. The system should be able to reduce memory consumption by sharing common base model weights, adapter weights, and states between PFT and inference. Following the design principle, we build LLMStation. LLMStation has 3 main components that work together to address the challenge mentioned previously. The first one is a novel iteration-level multitasking scheduling mechanism. The second one is a suspendable automatic differentiation engine. And the third one is an inference engine and fusion engine. And then in addition to this, we have some task queue that hold the incoming task, and then we have some memory manager to share the model and the states between 2 different workers. So the first one is, we will discuss is the LLMStation scheduler. It adopts a novel iteration-level multitasking scheduling mechanism, which improves PFT throughput by assigning proper number of PFT tasklets to be executed with the current inference iteration according to SLO. We will explain in the next slide that how can we decompose a PFT task into PFT tasklets. And then to achieve this scheduling mechanism, you need to obtain the latency of the PFT tasklet and inference task by estimation, profiling, or caching. So the details are included in the paper. And then with the given latency and SLO, the planner can calculate the PFT task list that can be executed together with inference task. So in this slide, we'll talk about how can we decompose the PFT task into PFT task lists. So before talking about our solution, I will have a brief description of the PyTorch Autograd engine. So the backward pass is done synchronously, and the gradient are calculated from the last layer to the first layer according to the computation graph. Once the backward pass starts, the PFT worker cannot adjust their execution according to the current workload. As a result, cannot realize the fine-grained scheduling algorithm we propose. So in the LLMStation Autograd engine, the function invoked in the function core chain of the backward pass are implemented as C++ stateless coroutine instead of normal function, with code a way to invoke other function. So you can invoke the PFT task and use a coroutine executor to voluntarily suspend and resume the backward pass. When a new backward pass task is created, LLMStation starts to execute it in a coroutine. And according to the workload, LLMStation scheduler uses planner to estimate how many layers of the backward pass could be executed together without violating SLOs. So decoding will meet the SLO requirement. And then we also have inference and fusion engine, which are optimized for this scenario. So when the PFT worker is in the backward pass, there's no way to fuse them. So you need to run them independently and in parallel. When the PFT worker is also in the forward pass, we can fuse the decoding phase and the PFT forward pass to amortize the data movement overhead because they share the same base model, which means you can reduce the data movement for hundreds gigabytes from HBM to SRAM. Then we also have do some experiment to evaluate the effectiveness of our system. We compare out-of-the-box solution, VRM pass torch tune, and optimized temporal sharing solution, PhiInfer, and optimized spatial sharing solution, trunk chaining. And we use some popular open source data sets and traces. So our first experiment evaluate the PFT throughput that different systems can achieve at different inference request way under commonly used SL targets. And then when the inference request rates are relatively low in serving Llama with RTX 3090, we can outperform other systems by up to 40 times because the temporal multiplexing solution does not co-executing different tasks and therefore cannot fully utilize the computational power. And the spatial multiplexing solution need to limit the compute percentage of the fine-tuning, so it can also reduce the max throughput it can get. And the trunk chaining, because it trunk the input into a different sequence and do multiple iteration for one step, so it will lead to slow down due to the additional data movement overheads. We also evaluate this system in lots of other settings, and the performance difference can be attributed to the reason I mentioned. And then we also started overheads of the suspend and resumes of the parameter iteration fine-tuning, and find that in single GPU fine-tuning, the overhead is low. In multi-GPU fine-tuning, the overhead is larger but not that high because there's some inter-process synchronization and in the fine-tuning. So in summary, we propose to multiplex resource in tuning and serving large language models, and our system can achieve high GPU utilization and guarantee the necessarily low latency. And at the end, we have the LLMStation, which consists of a free, very useful component that work together to address the challenge. And feel free to check the artifact and discover first. And thank you all the audience. Thank you so much.